Okay, 10.1, parametric equations. Parametric equations comes from the word parameters. And the idea behind this is that we've always worked with stuff in the rectangular coordinate system, Cartesian coordinate systems, where we have an x and a y that are related to each other. So every time I plot a point in the rectangular coordinate system, I've got a left move or a right move and an up or down move because that's built into my coordinates. What happens with parametric equations is that we kind of split it apart, and we have one equation that runs the move that's left or right, and then the other equation that moves the up and down, so that it takes two equations to get the same graph that we had before. And we're going to talk about how to do that. It's not a hard process. It's just a different process because there are some things that we can't graph on the graphing calculator, right? If it's got a y squared or square root of y or something like that, then I've got to solve it for y first, and it doesn't always translate nicely for something that I can graph. Well, with the parametric equations, if I put it in that form, then if I look at each piece separately, then a lot of times I can graph it more easily and I can work with it. You do use this in physics is mainly where you use these ideas. So if you will look on page 654 or 634, I can't see, it gives you the basic ideas of what's going on. And as you can see in example 2 there, the x and the y coordinates of the boat are. And they give you the x coordinate and they give you the y coordinate. Those are parametric equations because it tells you how you're moving separately, the two different equations. Okay? Most of the time that we do this in terms of time. Kind of like we did related rates. We're going to talk about this change that's happened in this position over a period of time. So how far has it moved left or right over a certain period of time as related to how far it's moved up or down related to that same amount of time. That's how we kind of keep it together. Everything's in terms of time. Okay? So in general, parametric equations have the form that x is going to be some function, g of t, and y is going to be given with some function, h of t. And normally that's going to be, you're going to talk about that graph in terms of some interval of time. So where it's going to give you a beginning point and an end point for the amount of time that's passed. So they take this x and y point that we had before, and they're going to turn it into a function of g of t, h of t, and it's for all the t's from A to B. So this is how it's written. So let's just look at one of those. Let's actually graph. Example 1, we're actually going to graph one of these. And it tells me that x is equal to g of t is equal to 2t. And y, which is our h of t, is equal to 1/2 t squared minus 4. And I'm going to do this for the t's from 0 to 8. Now this is how this works. To find this point, I've got to take this beginning point here, 0, and I put it in the x function. So 2 times 0 is 0. And you can do this the same way you've done it before. But I just use a different equation to find the y. To find the y, I put the 0 in for here, and I get -4. So my point on that for that graph, for this parametric equation, is 0, -4. And then I do the next for 1. So, oh, it's not there though. It's not x1, it's t of 1. So my x is 2 times 1, which is 2. And my y is 1 squared, which is 1, times a half, minus 4, which is a -3/2. Okay, so that point at 2 is -3/2. You see how this works? Okay, so you just take the t values that they give you, and you plug it in for t and for x. That gives you the x coordinate of your point. Plug it in for y, gives you the y coordinate of your point. And yep. So if you look at that, that gives you a curve, so something like this. Gives you a picture of it on figure 10.3 on page 635 if you'd like to look at all of it. Okay? Any questions about how to plot those points? Do I need to finish it out? All right, let's look at example 2. Example 2 is one of the reasons why we even worry with doing this. We're going to actually graph this equation. X is equal to 4 times the cosine of 2 pi t. Y is 4 times the sine of 2 pi times t. And I'm going to use numbers from 0 to 1. Now, the cool thing about this is the circle. And remember with the circle, I had to solve it for y and then take the square root and take the positive and negative half to get my calculator to actually graph this. Yes? Do y'all remember all that stuff? Well, if you will go get a graphing calculator or get your graphing calculator out, then I want to show you that you can actually put this in and get the calculator will now draw this if you have it in parametric form. I mean, you can go through here and you can like plot these points just like we did a while ago. Now, I'm not going to just use 0 and 1, right? I mean, if I were going to plot these points by hand, I'm going to have to use some fractions or some decimals to be able to get enough numbers to be able to actually draw this. But I want you to see how to do it with your calculator. So go to mode. Yep, go to mode. You do want it in radians, and you want it in parametric mode. Everybody see it? Yeah, it's right beside function. So put it in parametric. Now if you hit y equals, it should give you a place to put an x and a y. Okay? So now type this equation into the x1 and type the 4 times the sine of 2 pi times t into the y1. And it does put it in as t because in parametric form, t is our variable. Okay. And so you can also go to second graph to get the table, and you can look at those values. Okay. You probably have to go in and change your window. Well, didn't we just get through saying that we needed to change, the scale needs to be less than 1, right? Is that better? Now they go through and they give you in here a proof of this. But the nice thing about circles, again, we use these a lot because circles are one of the things that we like to be able to draw. They're very useful, but we can't draw it with a function grapher because they're not functions. But I can do them as a parametric equation. So if I have a circle that's like x minus x sub 0 squared, y minus y sub 0 squared is equal to a squared, right? That's our formula for the circle. Y'all remember that? Typically called it h and k and r, but it's the same thing. A squared, yeah, because remember r is got to be squared. Then I can always write this as a parametric equation. It's always x is equal to x sub 0 plus a times the cosine of b times t. And y is equal to y sub 0 plus a times the sine of b times t. And you have to figure out what the b is to make it to be the right. All b does is, if that's the period. So you can use anything. If you want it to generate it clockwise, you use it a positive. Wait a minute. Clockwise. I always get backwards. Clockwise is this way, right? So that one would have to have a negative 2 pi. And if I want it to do counterclockwise, that's a positive. Okay? But that's kind of like the period is what that tells us. Well, that's what b is. Okay? Remember, the 2 pi is the period of the entire sine function and the cosine function, right? It gets me back to where I started. And so when I'm working the other direction, what I have is I get the entire circle, or one revolution, which is 2 pi, when I take 2 pi and divide it by the absolute value of b. So if I'm using sine and cosine, then it's always going to be 2 pi. Because it takes 2 pi to get back all the way through the entire circle. You see what I'm saying? Okay. If it was tangent, we could probably use 1 pi, right? Yeah. Sure. It's great. All right. So let's just talk about doing that. Example 3. So we got this circular path. We got a turtle. It's walking with a constant speed in a counterclockwise direction on a circular track of radius 4 feet, centered at the origin. Okay, so I'm walking this direction. My radius is 4, right? Turtle's going that way. Starting from the point 4, 0. That's where we're starting from. The turtle completes 1 lap in 30 minutes. Their little legs are short. All right, so find the parametric description of the path of the turtle at any time t greater than 0. Okay, so we know that x is equal to 4 times the cosine of bt, right? Because my origin is 0, 0, so I'm not adding anything to it. Remember, that's my origin there. And this is my radius. Okay? And y is 4 times the sine of bt. Good. Now, what I got to figure out is what b is. That's what we were talking about a minute ago. Now, this time, they've given me a time. It says it can complete one whole circuit, which is 2 pi, right, in 30 minutes, right? So, if our t is varying from 0 to 30, our time from 0 minutes to 30 minutes, right, does a complete circle. In that time, we've gone, bt has gone from 0 to 2 pi, right? Therefore, 30b would have to be equal to that 2 pi, right? My time? T is time, remember. So I kind of turned it around. We had b times t. Now I've got t times b. You're all right with that, though, right? 30 minutes still means the same thing. All right, good deal. So that's a complete circle is what we're saying there. You get that? So b is equal to 2 pi divided by 30. Okay? And so if you reduce, because 30 minutes to do a complete circle, t is the amount of time, and I'm looking for b. So 30 times b has got to be equal to 2 pi, because it took 30 minutes to do one complete revolution. Okay? So if I reduce that, that gives me pi over 15. So 4 times the cosine of pi over 15, and I can't lose the t, you know. It's part of the formula. You're so very right. Yes. Yes. Remember, because in our definition, all right. So, any questions? All right. So we will always use 2 pi because that's our entire period. But if they give us a time, then we'll have to do that as our revolution. Right here? Remember you asked me a while ago, will I always use 2 pi? I will always, 2 pi won't always be the number I put in here for b, though. I will always use 2 pi. Yes. If they give me a measurement of time, then I've got to set it equal to the 2 pi. And the measure of time needs to be how long it takes to complete one lap or one complete unit, circular unit there. Okay? Is everybody good? All right. Now, let me tell you this. The only thing about parametric equations is you should always double check them because they're very straightforward for the most part, but sometimes they're just a little bit tricky. So you should always, anytime that you come up with an equation like this, you need to put this in your calculator and make sure. Every now and then, we actually have to go past 2 pi to be able to get all the points to make the complete circle. So when you put this in your calculator, just make sure that it draws a complete circle and make sure that we don't need to like go past 2 pi like another pi, do 3 pi or something. That's because of the every now and then, something that you do, you know, you think you've done it all exactly right. You should always check to make sure that you get one complete circuit. But it does go ahead and make you the entire circle. And your t's need to go from 0 to 30, right? For this to work. So you'll need to go into your window to make sure that your t's go from 0 to 30. you check your window and make sure your t went from 0 to 30? Thank you. Refrigerator. Good. All right, so that's how you do circles. Now we need to do parametric lines. Example 4 is for parametric lines. Yeah, you're done. You just wanted to come up with the equations to give you that circle. Okay, it says express the curve described by the equation y is equal to x sub 0 plus a times t. I'm sorry. X equals x sub 0 plus a times t, and y is equal to y sub 0 plus b times t in the form y is equal to f of x and we do have to assume that the x sub 0, y sub 0, a and b are all just numbers, and a is not equal to 0, and t is any number between negative and positive infinity. No, this is for a line, not a circle. Okay. So I've got two different equations, and it wants me to put this in the form of y equal to something times x. You with me? So in other words, where I've got this over here, I want some x's to be here. With me? All right. So I'm looking at this one. The y equals y sub 0 plus b times t. There's my equation I want to work with. But remember that I'm trying to put the x's back in, because parametric equations, I pulled the x move and the y move apart. Now I'm trying to put it back in. So how can I take this equation and somehow substitute it into this equation? T is in common, right? So if I take this equation and I solve it for t, I've got x minus x sub 0 is equal to a times t, right? I subtracted x sub 0 from both sides. And now I've got to divide by a. So now that this is equal to t, I can take this equation and substitute that in. And now I've got both equations in one. Now, I don't know if you noticed anything there or not. Doesn't look like anything interesting to you. There's a y on both sides. Slope, intercept form of the line, right? Or a point slope. Actually, it looks more like the point slope, right? Slope. Here's my slope. Here's my point. Da, 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 da. So, you just proved that if I have a line, and I have the equation of a line, and if I want to put it in parametric form, this has to be true. Okay? Very good. So y'all get that? All connect. All right. So You good? All right, because we'll do that the same way. Okay, example 5. One of the reasons why we do this is because when you get on further on in calculus, a lot of times you have to be able to what we call parameterize curves. Okay, so let's talk about, in other words, they're going to give you the curve and you've got to turn it into parametric equations. Okay? Fantastic. All right, so we have got y equals 9 minus x squared for the x's between -1 and 3. All right. So we want to turn this into a parametric equation, right? So this is a good idea, actually. Okay? The easiest way to do that is to let x be equal to t. Because if x is equal to t, then without having to do any of that substituting in and simplifying and what you were talking about just a second ago. But think about it for a minute. Do you see how that's going to work for me now? And then my t is just going to go from there. Huh? Okay. You can change other stuff. I mean, if you want to make this be t minus 1, you can make x be t minus 1 and then just put t minus 1 in here and simplify it. And no, can't do that. We want to do x in terms of t and y in terms of t, right? Do you understand what I said, though? If you make this be t minus 1 or t plus 1 or whatever, you still have to plug it in for the x and simplify to find out what the y function would be in terms of that t. And I'm not actually circling stuff? All right. But anyway, that's not the only one. Like I say, you can pick anything you want. This is just the easy way to do it. If you want to, but I'm not going to. Okay? Part B. On Part B, we get the equation x is equal to y minus 5 squared plus the square root of y. Now, this time, y appears twice. So I really don't want to do the whole thing with the x being the t. It would be easier to let y be t. If you want to. Okay? Now, I want you to notice here that we've talked about intervals before, and I don't have anything written on this, but what numbers can I use for t here? I have a restriction on my domain. Only positive, because I can't have a negative square root. So my interval here is from 0 to infinity. Or, if you want to write that in interval notation. Okay? And again, it's always a good idea, once you do this, to double check it in your calculator to make sure that it actually draws the same picture that it's supposed to. Because it is easy to kind of say, this is not a hard process, but it is easy sometimes to have made a small arithmetic mistake or something and you have to fix. So it's always a good idea to just double check stuff. No. No. Yes, two different problems completely. Did I mess up? Okay. I was just showing you some different ones on how to do this. I just wanted to show you the different. Yeah. Don't want you to think you always have to let x be the t. You do the one that makes it easier. That's why I always make sure and show you those. All right. So C. All right. Now we're going to do a piecewise linear path that's connecting these points from P to Q to R. Sorry, no F. And we're going to do them in that order. So I'm going to draw my picture of this over here so I can kind of see what's going on. So I'm going to go from P to Q to R. Okay? I'm going to put little arrows kind of in there to help us remember the direction we were supposed to be going. Because when you draw all those, I don't know if you graphed one of those parametric equations a while ago when we were playing with the calculator, but you can see the direction that it's plotting the points in. We tell it the direction to go in. Piecewise function, and we're going to have two different things. We're going to have an x and a y for this one, and we're going to have an x and a y for this one because it is piecewise. I can't do it all at once. Now, y'all proved a while ago on here on the board that we can always take lines, and that's what these are, and write them in the form that x is equal to x sub 0 plus a times t, and y is equal to y sub 0 plus some b times t. Right? Remember when we did that a second ago? We're going to actually use it now. Okay? So, we are originating here at this point, negative 2, 0. So you always start with your point where you're, that's what subscript of 0 means, is where you started. Okay, so if we're going in the direction from P to Q, P is our origination point. That's our x sub 0 and y sub 0. Okay? All right? And we need the slope. Okay, so our slope for this line is 3 over 2. Okay? So, when we do this, so my x is my original x plus the part of the slope that has to do with x, which is 2 times t. And our y, slope, y over x. So I use the denominator because that's got to do with x. To change. Yeah. Wasn't that what we had a while ago when we did it? Yes, we did. I'm pretty sure I pulled it out, b over a. Okay, so we're good? Did I not make that connection earlier for you? I'm sorry if I forgot. Yeah, your b and your a come from this slope right here. Okay, good. So I did say it, I just maybe not loud enough or something. All right. I was thinking it. Does that count? Okay. And then we do y the same way. We take the y coordinate of the original point, or the place plus 3t, because it's the y part of the slope. And this happens for all x's for all t's from 0 to, now, this is the part that you got to pay attention to. Remember, I'm going to plug t back in here, but I don't want to get a point past this point right here. Okay, so I know 0 works because I fixed it so 0 works for the first one, right? Because if I put a 0 in here, I'm going to get the point -2, 0. I fixed that. It needs to go to the point 0, 3. So what would give me 0 here if t was, how about a positive 1, right? And if it was positive 1 here, I would be at 3. That's how you get your endpoints for your t when you do a piecewise. Okay? And then now we're going to do the same thing with this other half, this other piece that starts at 0, 3, has a slope of -3 over 4, right? And so we've got, tell me what it is, x equals plus 4t, and y equals, or minus 3t. Okay, good. Well, I want it to go from, I can't do it from here because from 0 to 1 I'm doing this piece. So I need this to start at 1. You know what I'm saying? So I got to go back and I got to kind of work my way backwards here. So if I put a 1 in for this, I'm not good, right? Because that'll give me 4, so I may have to add, I need that to be a -4 there, right? Because I want it to be 0. When I put my first number in, I want this, whatever it is, to give me 0. Just going to in a minute. This is a piecewise function. If I've already used from 0 to 1, this one's got to start at 1. So I got my basic formula, but then sometimes you got to go in and play with it to make it work the way you want it to do. Okay? So if I just left this as a 1, that'd be 0 plus 4 times 1, which would be 4. So I can add -4 to it. Because that's what it took to add to 0. Because I want my t to be 1, and I know my slope's got to be there. I can't change my slope. I can change that original point thing. Okay? Piecewise functions, remember. I can kind of think about what it would be doing over there, but not draw it. Okay, now, hold on a minute. Now I need to play with this one, possibly, right? Because I need this to be 3, and if 1 is, so I need to make that 3 a 6. I'm still just getting this original point. If I put t of 1, which is where I've got to start from since I've finished up the last piece at 1. Yep. We have to alter this so that I get the original point when I plug in the first t value. whatever we have to do to it. Now, this should be good, but we always have to double check it. All right? Now, I want it to end at the point 4, 0, right? So, for this to be a 4, then this t would need to be a 2, right? Okay? Because -4 plus 8 would give me +4. And let's see what happens here when I put the 2 in here. So I get 6 minus 6, which would be my 0. So this is it. So my piecewise function here, when you're doing parametrics, they're much bigger, is I have x is equal to -2 plus 2t. Move it down a little bit. I'm fixing to run into it. And y is equal to 3t from t's from 0 to 1. And then I'll have x is equal to -4 plus 4t. And y is equal to 6 minus 3t from 1 to 2. So it's always a good idea to check those endpoints to make sure that the formula that you've come up with, because there is more than one formula. There's more than one way to do it. Okay? Any questions about how to get parametric equations from general equations? All right, well, now let's talk about the derivative. So, if we let x be g of t and y be h of t, and g and h both have to be differentiable on the interval that we're talking about, okay? Then the derivative of y with respect to x is equal to the derivative of y with respect to t divided by the derivative of x with respect with t, because, right, we've got t's in our equation. And so basically, I want the derivative of y with respect to x, and I take the derivative of the y function with respect to t and put it over the derivative of the x function with respect to t. Okay? Now, why do we use derivatives? What would be an application of a derivative that we've been doing? Maybe wanting a slope, right? Slope of a tangent line to one of these parametric curves. So example 8 does that for us. Part A says I've got x is equal to t and y is equal to 2 times the square root of t for all t is greater than or equal to 0. And we want to find the slope. Any slope that's horizontal or vertical tangent line. So we want any horizontal or vertical line tangent. Okay. So we just want to know, does it have any? It's got any place where it's got a horizontal tangent line? That means the slope is 0, right? And a vertical line has a slope of undefined. Okay? So to find the slope, we take the derivatives, right? That's what we've been doing. So if I want the derivative of x, y with respect to x, dy dx, I need the derivative of the y function So the derivative of the y function, we got 2 times t to the 1/2, right? That's not y prime, though. It's just y rewritten. And now let's take the derivative of that. So I've got 1/2 times 2 times t to the negative 1/2, right? So these 2 times 1/2 cancels out, and so I'm left with 1 over the square root of t. And the derivative of x with respect to t is 1. Get, because it's t to the negative 1/2 power. So it puts it in the denominator. So dy is 1 over the square root of t over 1, which is 1 over the square root of t. Right? As long as it's greater than 0. Okay? So, is there any way that I can make, when I have a fraction, how do I make it equal to 0? It's got to be 0 in the numerator, right, in the top. So is there any way I can make a 1 into a 0? Can 1 over the square root of t ever be equal to 0? No. So there are no horizontal asymptotes. Or no horizontal tangent line. Sorry, I was doing asymptotes in a different class. College algebra. Okay? Okay, now do I have a vertical tangent though? That'd be a 0 in the denominator. So if t was equal to 0, I would have a vertical tangent. So it's at the point 0, 0. We have a vertical tangent. Okay, so any questions about what you're going to do with those ideas? When t is 0, it gives you the point 0, 0. Okay, because remember, I put it back into my original equation. X is t, so if t is 0, x is 0. And y is 2 times the square root of 0, which would give me 0. You do have to go back to the original equation to find your point where your vertical or your horizontal tangent line actually sits. Okay? Any questions? That's all there is to parametric stuff. Okay? First of all, I just had to teach you how to do parametric because we had never done that before, but then the derivatives is what it's actually supposed to be new in this class. Not hard? All right. The last section in this chapter, which is the other piece that we've got to get done today, is the stuff on conic sections. Anybody remember what conic sections are? Remember that word? They're the circles. What else? The ovals, called ellipses. Not polar graphs, conic sections. Yep, it's 10.4. No, that's the polar graph. Conic sections are the parabolas. Conic sections are where if you had cones and you sliced through them with a plane, the different shapes that you would get. So if you have a cone here, think about it for a minute. If I slice through it, I'm going to get a parabola if I slice this way. Right? Think about slicing through there this way. See, it would give you that parabola right there. That's what I'd cut off. I sliced it right there. You'd have a parabola that piece would fall off. Yes.
Oh, if you put it on its side?
Yep. Let me put it on my side. Well, I don't necessarily have to cut it in half. I can slice it anywhere vertically, and it's going to make me a parabola shape that's the shape that's left over there.
Oh, I get what you're saying now.
Okay. And then we can also get a circle. If I slice it horizontally, exactly even to the parallel to the base, it's going to give me a circle of different sizes depending on where I slice it. I can get an ellipse if I slice it so that it's not parallel to the base. It'll kind of go through at an angle. It's going to give me an ellipse. And then I can get a hyperbola. Now the hyperbola takes two cones, one on top of the other, to slice through. And they have pictures of that for you on page 665 if you want to look at those. And we did do this in Algebra 2. This is not new. I'm just going to remind you about these formulas. Because the college says we did. Okay, so the equations for parabolas and all the characteristics of a parabolas are on page 665 in a box. The equations for ellipses are in a box on page 667. And we'll go back and look at these in a second. The equations for the hyperbolas are on page 669. And then circles, we've already talked about equations of circles, so they don't necessarily do them here. But I can give it to you if you want the equation for circles. They're always x minus h squared y minus k squared is equal to r squared. Yeah, we've got that already, so I wrote it again. Center. So that's the center of the circle. Just like the x sub 0 and the y sub 0 were just the center. Yeah. Okay. And that's just using those formulas and that information that's given in those boxes on those places on those particular types of problems. They're going to expect you to be able to take the equation of a conic section and be able to use that to get a graph. They're going to expect you to be able to take the information from a graph and be able to come up with an equation, just plugging it back and forth into the formulas. Okay, that's all there is in that section. Any questions? All right.